Cooking? We're cooking. Okay. Got it. All right. So this is CS. What? What? Yes. So this is CSC548, which is like a computer organization infrastructure type class. So now I know Curcio is currently in the undergrad organization and architecture class. Who has had an organization class before? So you had old Alex. Did you have one?
Was that one of the undergrad classes?
Not necessarily. It's not required.
Oh, it's not? Which one is it? I'm pretty sure it's
It,
required.
not when some of them went through. Have you had an organization architecture class before? I think your name is your name Tim.
Yes.
Have you had one?
No.
Okay. Have you had one? Okay. Are you taking the undergrad one? Okay. Oh, so this should be entertaining, I suppose. All right. So I guess just while we're at it, since obviously I know all those guys and don't know you, why don't you give me a little bit? Well, introduce yourself to the women, to the ladies, and so what's your background? What have you done? Give me the 30-second version.
My name is Tim. I live in Port Washington, Wisconsin, just up the road. I just graduated from Bethany Lutheran College in Mankato, Minnesota. I majored in math, and I haven't had formal computer science, but I've been, last summer I did some research that was mostly all coding, and I decided to do computer science.
Okay. What kind of programming did you do?
R.
Okay, gotcha. What kind of projects did you work on with it?
It was research with biostatistics.
Okay.
Trying to come up with a new method to do something that's never been done before. So.
Okay. But other than that, no computer science background.
I taught myself Python and then did an introduction to programming 2 class.
Okay, gotcha. Okay, so you're probably about on equal playing field with old Alex. He's had a complete computer science degree, but. Yeah, so that's old Alex. He's from Vietnam. His name is not Alex.
Is it now?
Huh?
It is now.
Legally, you changed legally?
Yeah.
Because nobody could pronounce your actual.
His parents had a tough time. Part
It's-
of it.
Oh. And this is our other Tim. He just graduated undergrad computer science this last semester.
Oh crap.
Wait, we good? Recording didn't break.
I'm Cinnamon.
Yeah, that's Cinnamon. So that's Josh Curcio. I named him Cinnamon last semester.
What was the story behind that? I missed that.
I don't know if there is a story actually.
What's the story, Cinnamon?
He said I was thinking about you one day, and all of a sudden I thought stripper and Cinnamon. Okay.
Invalid scan feed.
Right.
Hold on.
Does he have a nickname now?
Brian, I don't think I have it. Brian doesn't have it. It's not special.
All right, and this is Emo. He plays sand volleyball.
Okay. That works.
Okay. So now that we've had the
Why is
inter,
he emo?
that's his last name. Well, now you're just getting all judgy.
Yeah.
All right.
Blue hair.
All right, so let's start talking about stuff. So basically, the only one in here who's had any organization class is Tim, and one day for so I should probably kind of assume zero knowledge. All right. So that's fine. Huh?
You taught me so far.
Well, that's going to be like maybe the first like half hour in here. Then we're going to keep going. All right. So let's start off. So let's talk about the syllabus and stuff first, and then we'll talk about the book, and stuff. We'll talk about stuff. All right, so I'll open up the syllabus here. So as we have a extremely detailed course description for this class. I wonder, can I zoom that in? There we go. So theory and design of computer hardware, data representations, operating systems, computer networks, runtime environments, and peripheral devices. Students will configure and interface software with all of these entities. All right, so this is where things get a little bit interesting. So in the undergrad course, we have a computer organization and architecture class where we really talk about the human being, well, how we interface directly with the processor. That's a component of what we'll be talking about in here. What we're also going to be talking about in here is how the various portions of the computer, the CPU talks to the operating system, how the CPU talks to memory, how memory talks to the operating system, and all these other pieces. So we're looking at a little bit larger world in here. Specifically, we'd be looking at some things like assembly language, and I'll kind of swing back and we'll fill in some of the gaps since most of you really haven't had any background in this stuff. So more important stuff. Oh, look. Tuesday, Thursday, this class, so. I must have copied them both off the same other syllabus. Yeah. So grading, 45% of your grade is homework assignments. Homework assignments in here are going to come in two flavors. We're going to have, every week you'll have 2 assignments. So you're going to have kind of either a programming or a computer architecture organization, like kind of short answer type homework assignment, and then there's going to be a paper every single week. So part of that has to do with the grad program already has an accreditation, which has a rating component, so have to do lots of papers. And then we're also adding another accreditation with ABET this semester, and there's a rating component with that. So that's where you get your 6 credit hours in. So each week expect to be writing lots of papers. And I'll try to keep the papers like 2 to 3 pages, but on some sort of interesting architecture organization topic. And then I'll make the other homework assignments, they're going to be kind of all over the place in terms of complexity, because we're going to be writing some stuff that talks to the CPU, and we're going to need to use like a Linux operating system to do that. And we might have other things that makes more sense to do kind of short answer, because we're talking about kind of theoretical things that we can't really test without like things, without things. So we'll kind of shoot from the hip with those. We will have potentially pop quizzes in here. I would probably expect to have a quiz every class, since we only meet once a week. So more than likely we'll come in and we'll spend the first 10 minutes of class having a short quiz covering something that we talked about the previous class. That's 15% of your grade. Sometimes I'll be nice and give you kind of a hint on the quiz the previous class. So like maybe today I might like make a mention like, oh, this might make a pretty good quiz question for next class. I may also give hints on the quiz via Slack. So if you guys want to make use of our Slack channel, which I'll talk about here in a second, maybe on Mondays or something, you might choose to do a public message on Slack, and I might give you a hint on what the quiz might be, because that will be kind of my reminder of think about what the quiz should be. So maybe I'll tell you what maybe the quiz might be covering to give you a little focus. So that'll be kind of on you. So to join our Slack channel, and here I'll go ahead and create our, so this is 548. Is that right? CSC548. Huh? Okay, I got that. There's not a 325. I'll create that while I'm at it. All right, so for those of you who don't already have a Slack account with us, the website you'll go to is cuwcs.slack.com. And you should be able to put in your cuw.edu email address. And I think you could pick whatever password you want to sign in. I'm not 100% positive, actually. It'll probably ask you to create an account. But then you'll get into the account, and at the very least, I would say join any channel that looks interesting, but definitely join the CSC548. Have you used Slack before? Okay, so Slack is like basically a chat program, but there's native apps for Apple. So this is the app off the App Store, the one I'm using right here. Windows as well as mobile, so iOS and Android. And for the mobile ones, you can get push notifications. So you can set up push notifications for the 548 channel. So whenever I put anything out there, or somebody else puts something out there, you'll get a push notification on your phone letting you know something has happened. Okay. So that's our Slack channel. Let's go back. All right, so 45% will be homework, 15% will be quizzes. We'll have 2 tests in here, a midterm and a final, and as it is with all of my classes, if you do poorly on the midterm and you do better on the final, I'll replace your midterm grade with your final exam grade. So midterms will be kind of around week 8, give or take. Final exam will definitely be during final exam week. So that's the scoop with that. I won't go the other direction. So if you you ace the midterm and bomb the final, you're going to be out of luck. So yeah, I'll only replace your midterm with your final grade. All right, so that's your how the course is graded stuff. Questions on that?
Still accepting bribes?
I always accept bribes. I mean, I have to equally distribute the wealth to the benefit of the bribe to everybody, because you have to treat everybody the same, but my pockets will be lined, yes. Only 5, we could do a group pool. All right. Bitcoin. Everybody doing it.
Like Pebbles, just like, pinning 20 tests.
That's right. All right, so questions about the syllabus? Pretty straightforward, nothing crazy there. All right, so let's go back here. So let's talk about our textbook next, I guess. So this goes with our ABET accreditation stuff that we are going through now. So we need a book that allows us to monitor assessment, how people are using the books. So we're using this place called zybooks.com. So if you go to zybooks.com, it'll take you to something that looks kind of like this. And you are going to click on subscribe. I'm already logged in to the thing, but you'll click on sign into zybooks.com, so you'll create an account. You'll enter this code, CUWCS548, Littman Fall 2016, and that'll allow you to subscribe to the book for this class. Then click subscribe. Cinnamon, you should not subscribe to this one because you already have it from the other class. You only need it once. So in any case, that will get you the book, and the book is kind of an interactive text. So here, let me bring it up in here. And we will be looking at the book some today as well, since we have 4 wonderful hours together. All right, so it looks like the book has a cost of $83, and that subscribes you to the book until, looks like, right after the first of the year. Yours was $1 cheaper? Really?
Yeah.
How does that work?
I don't know.
Maybe he's got a returning student discount for $1.
That's weird.
Maybe that's tax.
Because they should be identical. Oh, you know what? They actually might. No, they are. They are identical. They're identical. Because I almost did a different section in this one, but I didn't. Because we're not only using the, okay, whatever. Just, it's fine. So anyways, you'll subscribe to the book. The book has all these chapters, and we'll be looking at, actually, you know what? Let me just double check something here real quick.
Make sure I get the right one.
Yeah, you haven't bought either of them yet?
No.
Okay. 19, yeah, it's the same. They're the same.
That's the one you just clicked on.
No.
Oh.
This is 548. The other one was 325.
Oh. Did it say it was $1 difference on
No, let's see. It does. I wonder what the deal is. Oh, well, whatever. All right. So, anyways, you'll get the textbook. So when you look at the textbook, so I'll just go to our first chapter here, Computer Abstract Technology. We'll go to Introduction, and we're going to start talking about some of this stuff today. So we will use the textbook in class, but some of it, like I'm not going to sit here and just read this stuff to you. We'll kind of bounce back and forth, but we might use some of these exercises that are in here. So one of the nice things about the textbook as you go through it is there's some interactive things. Some of them are like little quizzes like this, and other things are actually more hands-on, like almost like program something, build a circuit to do something, that kind of stuff. It gives you a way to kind of go through the class in a different way than we typically do in the classroom. I'm also, because of our accreditation stuff, we're changing how we're going to deal with class. It probably is going to benefit you. Typically the way I've taught the grad classes is I go 4 hours and take a 20-minute, well, 2 hours, take a 20-minute break, and then go another hour and 40 minutes, and it's all talking. We're going to take breaks more often, and we're also going to do more in-class exercises where you can break into groups or something like that, or I'll give you guys a problem to solve and that kind of stuff. So something that will hopefully break up the monotony inside your brains a little bit. So we'll give that a shot. I've been teaching for 18 years and never really done that, so this will be an adventure. This will be an adventure together, but we'll see how well I can stick to that. But I don't know, some research that we went through in our faculty development stuff indicates that I guess students can only pay attention for 50 minutes at a clip. It's like a thing. Anything beyond 50 minutes and you're gone. And actually, if you're just listening to lecture, it's more like 20 minutes before you just zone out.
There's a step further than that. That's lecture and then debugging, which is 5.
So yeah, you're just gone. Yeah, okay. So we'll see how it goes. So in any case, there's some interaction with the book as you go through it. And one of the things that we need for our accreditation is a book like this keeps track of student progress through the book. So it's not so much that this is a graded activity for you. You can answer these quizzes the wrong way as much as you want. You can just keep guessing at the answers or something. But we will be gathering assessment information about how you're using it and that kind of stuff. So that all goes to making your degree worth more. It's the idea with the ABET accreditation stuff. Okay, so we'll come back to the textbook here in a few minutes as we start going through some of this stuff and talking about it. I'm going to talk about things at a higher level first. Let's go back here. We'll go into, we're going to look at the assembly language tutorial here in a minute as well. But before we do that, let's go into assignments. Oh, I get 2 of these? So why is there 2 of them? There we go. Now there's just one of them. All right, so a couple of things here. So no late work will be accepted unless there's real emergencies. So get everything in. I mean, you have a week to work on your stuff. So get it in ahead of the 6 p.m. start time for the course. I mean, if there's a true medical emergency or something like that, then, we can deal with that on a case-by-case basis. But something like, oh, they changed my work schedule, that's not an excuse. I get it. Real life sometimes gets in the way, but that's not my problem. That's somebody else's problem. So nothing late. Now, for every homework assignment you submit, I'll say in here, except for the papers. It's kind of be stupid to submit this for the papers, but if you feel it would help you with the paper, you can. So I have this self-assessment thing. So they ask 4 questions. So what I want you to do is for every assignment, copy these 4 questions, paste it into the submission box for the the homework and answer them. So what I want to know is how long did you spend on the assignment? Based on your effort, what would you give yourself? Based on what you actually submitted, what would you give yourself? So those two things specifically in computer science sometimes don't line up, right? You might spend 10 hours on something and have very little to show for it. I want to know, so really number 4 is the most important one. That's tell me about your experience in doing it. You know, if you spent 10 hours on it, explain to me what things you tried, where you struggled, blah, 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 that kind of stuff, so that I can award partial credit in an event that you have very little actual work to submit to me if things weren't going well. You don't have to turn this in for the papers, but if you really have trouble on a topic for a paper and you think this would benefit you, you should probably do that. But I'm not going to dock you points if you don't turn this in for the papers, but you should turn it in for all normal assignments. All right, or I'll just give you a 0. So that's the deal. All right, questions about that? Makes sense. So we'll all do our self-assessment daily for all non-paper assignments. Okay. And then lastly, let's go back here. We're going to be working through this assembly language tutorial, and this is really strange. This, oh, there we go. So we're going to be spending part of our class each week working through some of the things in here. So, and this could be a little bit different than what we're doing in the undergrad course. We actually have somebody in here who's taking both courses. So there's going to be about 15% overlap in those, but then we're going to go in some different directions in here. So every one of our courses is going to be looking at things from a couple of different angles for us, because we're looking at the bigger picture of how computers work, how the hardware all works together and things like that. So we'll spend a little bit here during our first kind of, let's say our next 30 minutes or so, kind of introducing this idea of computer organization and architecture and what assembly language is and that kind of stuff to kind of figure out where on the map we are. And then we'll take a little break and we'll come back and start dabbling. All right. So let's start off with, open up a slide set here. Probably should have named this guy CSC548. Okay, so that should be good. And then I'm going to duplicate this. Okay, so we're going to draw some pictures here. Actually, I want to go a little bit deeper than we did in the other class. So when we think about our computer, let's start getting the big pieces of our computer. So I'll get us started off here. So we have the CPU. What are the other components that make up our computer? Graphics card. Okay, so we'll call that guy the GPU. All right, what else? Downloadable RAM? I don't even know what that means.
It's like the joke people who don't know computers say. It's like, I'm going to download more RAM.
Oh, I got you.
More RAM. Just download it.
I got you. All right, what else? What else we got? Hard drive. Okay. All right, what else?
Motherboard.
Okay. All right, I'm actually we'll spell that out. Okay. What else? PESU?
No,
PSU? Okay. That's probably not actually needed
that's
in.
what's in a computer.
Yeah, that's not one of our large elements. Okay. RAM. Yeah, that one belongs. Okay, so really I/O devices. Probably we just capture that as one big big dealio. I/O devs. Okay, let's kind of leave it at that. We might actually end up throwing a couple other things or exploding this out a little bit and like maybe put monitor in there because that's always a thing, and also keyboard is always a thing. But all right, so these are the components of our computer that kind of make the computer all work. And what we're interested in is how do all these things work together? What role do each of these play? And we're going to spend quite a bit of time talking about the role of the CPU. Probably a pretty important part of the whole thing, kind of like the heart of what's going on. But it's also probably one of the least understood elements of the computer. It's one of those things where like, oh yeah, it's just the processor, or you need a better processor, you need a faster processor, but kind of what does that mean? What does the speed of a processor mean? What is the actual job of a processor? All right, so outside of the CPU, we're going to kind of come back and deal with the CPU here at the end of this discussion, but let's just talk about the motherboard first. Tell me, what's the job of the motherboard? Okay. So what do you mean by house everything?
Like everything connects to it so that everything can communicate.
Okay, so could we really talk about this guy as basically being like the communication highway that all of these individual pieces use to communicate with each other? So this is really nothing more than a way of providing power to these individual devices, get electricity to them. That way you don't have to do individual plugs to each of your things, even though some of them do work that way. But the motherboard has a power source coming into it, then it delivers power to the other pieces. But most importantly for the motherboard, it has something called a bus. And that bus is a communication channel that links all the different parts together. Okay? So yeah, we'll just kind of leave it at that at the high level for right now. All right, so without the motherboard, our various components up here couldn't talk to each other. Pretty important piece. Okay, so let's go, we'll get GPU and RAM and HDD out of the way real quick. So what's GPU? Okay, what's that guy's job? What does he do? Okay, so he's going to interface between, so this is where I said I was going to probably go ahead and throw monitor out there. So he's going to be an interface between the monitor and the processor and RAM. Okay, so those three guys work together. Things get housed in RAM, move on to the GPU. The GPU then also has its own RAM, so we can almost take this GPU, if we change it to say graphics card, we could redraw this exact same thing minus the hard drive, but they do have their own storage for a graphics card. A graphics card in and of itself is a computer. Okay, so the job of the GPU is to be a domain-specific computer, that is to make stuff show up on the monitor based on what the CPU says to the RAM and the GPU directly. Okay, what about the RAM? What's its job? Okay, define very quickly. Okay, that's a good safe answer. So yeah, definitely faster than the hard drive. So RAM is faster than the hard drive. Are there portions of memory on your computer that are faster than RAM? Okay, do you know of any of those? Okay, anything faster than that? Kind of probably, but okay. So RAM is a shared resource that everything of the computer, every your software applications, your operating system, all these different components we have here, they're all sharing this one resource. And I think it's fair to say that this is considered to be relatively fast in general terms. So much faster than storing stuff on the hard drive. So we would say that this is long-term storage, this is short-term storage that needs to be fast, but maybe not ultra fast. Something in that ballpark. Okay, but from our perspective, the more important thing is this is a shared resource for everything. All right, and we'll forget about I/O devs for now. This is just ways of getting crap into the computer and ways of showing stuff to us. All right. Now the CPU is where things start getting interesting for us. It obviously is the core for all of these things. And really, you can say CPU and GPU, as I have it written here, are equivalents to each other, but GPU is more specialized. So let's kind of talk about that for a few minutes. CPU versus GPU. So you already told me a little bit about the graphics card and the GPU, and we kind of generalized said that it just makes stuff show up on the screen. But what specifically does the graphics processing unit do? What kinds of things do you suspect that the CPU for your graphics card does?
GPU is much faster matrix multiplication.
Okay, so it does math stuff, right? So the GPU doesn't have all the extra bells and whistles that our CPU has. Our CPU is built to be a general purpose problem solver. Well, really a general purpose tool through which we solve problems. But the GPU doesn't do that. It doesn't have 4,000 magic tricks to do all sorts of different stuff. It knows how to do like a handful of things. It just knows how to do those really fast. Okay? So the whole job of the GPU is to do floating point math. That's at the end of the day, that's its job. Now, beyond that, some interesting comparisons. When I say multi-core, what is that? What do I mean by that? When I say a processor is a multi-core processor, what does that mean? Okay, more than one CPU, more than one GPU, something like that. All right, so when we talk about CPUs, so let's just do multi-core here. What's your common number of cores a CPU has? So 4 isn't unheard of. Dual core probably at least. We do have like 6 and 8 cores, octa-cores, right? Okay, but 4 core, so let's just say 2, 4, 6, 8, something like that. Is the number of cores you might have in a processor, and we'll come back to that here in a second. What about GPUs? What do you think? Okay, like give me a number. 16 or 32? Could be, easily could be. Yeah, probably your latest processors are maybe 2048 number of individual cores, something like that. Certainly 1024 cores is a thing. So let's just use that as an example. 1024 cores. All right, so that means that a GPU can do 1024 calculations simultaneously. Something like that, right? You know, and in every 15 minutes when a new graphics card comes out, they're probably going to throw more cores in there, or come up with better ways of using the core through some architecture type stuff. One thing's called pipelining that we'll talk about in here as well, that we won't talk about in the undergrad class, but different tricks that we can take a single core and make it seem like it's faster.
The newest GTX 10 series is 2,500 cores.
Actually, it says 2,500. That's a very
2560.
Oh, that's a very weird number. Yeah, I would have guessed it was 2560 minus 2048. What is that? 2560 minus 2048. Yeah, that's a power too. So it makes sense. I'm not the math guy. He's our backup. Huh? Oh yeah, you too. Yeah, man. My math prowess disappeared, I don't know, 15 years ago or so. Everything just kind of slows down. That's like vegetable lasagna now, I guess. Do you even get that reference? Seinfeld. It's a Seinfeld reference. Do you even know what Seinfeld is?
Yes.
All right. So, in any case, we have many more cores in our GPUs than we do in our CPUs today. Does that mean our GPUs are bigger than CPUs, physically in size? Do we? Are they? So we got to kind of think about it from a hardware perspective. What actually is the GPU? Where does the graphics card end and the GPU starts? Graphics card is really kind of a catch-all term, right? It's the thing you take out of the box that you just spent, you know, $500, $600, $700 on that has fans all over it, right? Okay, why does it need so many fans? Because of all the math, right? So we have thousands of cores, and those thousands of cores are all doing simultaneous math. It gets hot, okay? And that's going to be a theme that we come back to multiple times throughout this course is the biggest enemy of hardware is heat. Right? The reason why our processors aren't faster today, heat. The reason, all this stuff, it's all heat. If you didn't have a fan on your CPU would probably burn up within 5 or 6 seconds.
Didn't you do that?
That was years ago, and it wasn't me. It was a college buddy of mine.
Yeah, he overclocked it.
Yeah, he was overclocking like a 200 megahertz Celeron processor to I think 1.6 gigahertz, and like in his room, he just had this like fan blowing on the thing. It's like 4 a.m. He comes down to my dorm room. He says, "It's like I have a problem." And I look out the door. There is flames billowing out of his room. I mean, his room looks like the entrance to hell. This isn't like a little smoke. His room was on fire. The whole room was on fire. So yeah, so that was overclocking gone wrong. A lot of our modern motherboards have they have their own sensors on it. So if you try to turn your motherboard on without a fan hooked up, it just won't turn on. It won't power up because it knows something's not right, or it'll stop as well. Apple, especially their laptops, have some of the most annoying. More times than not, it probably saves you, but it is kind of annoying, some of their power management, heat management stuff, where if it trips, you won't even be able to get your machine back on. It almost forces you to take it into an Apple store unless you know like the secret like 9-button, Klingon code you have to put in to like reset the reset either the like, it's not the BIOS. There's one for the memory battery management. I think it's Power Services, PSU, and then there's another one that deals with the heat sensors, and nothing will turn on if you don't reset those. So when you go in, it makes Apple, the Genius Bar makes them look like it, geniuses, where you walk in and you're like, this thing's bricked, it's completely dead, and they need to get like 4 employees over to hit enough buttons, and all of a sudden the thing just boots. everything's good. So in any case, heat's kind of our enemy, and that's going to be a common thing we're going to keep coming back to here. But the question I'd ask is about the physical size of our GPU versus the CPU. So when you look at that graphics card, when we take it out of the box, we have, let's actually bring a picture of it up. What's our latest, greatest? GTX 1080. All right, let's get an image of this guy. You see, look, these things look like sports cars. All right, so this is good enough. All right, so there's our graphics card. Somewhere in there's a GPU, right? Actually, somewhere in there's 2,500 GPUs because it's a multi-core GPU. So what percent of that do you think is the actual GPU? A small percent? Yeah, it's probably more than 5%, but small, right? A small percentage. A majority of what we're dealing with here is heat sink and then heat dissipation with the fan. Okay, that's a majority of what we're dealing with. And that's it. I mean, this part down here, this is the interface with the motherboard. That's all just, hey, we need to be able to talk to the other stuff, so I need to plug into the highway, the communication channel that we talked about. So that's the only job of that part right there. The rest of this is all heat dissipation, except for the 2,500 cores. Okay, so now the 2,500 core chip is likely no bigger than a Core i7 processor. Now, where things get a little bit weird with graphics processing is since consumers like us aren't the ones built. I mean, I guess technically, if you really wanted to, you could make your own graphics card. Nobody does it, but there's no reason why you couldn't. I mean, they do it, right? But
Would you be really
Yeah, well, consumers don't make graphics cards, right? So we don't need to worry about standards. So, for example, if you are building your own computer, how many of you have built your own computer before? Okay. So if you were to get a Core i5 or a Core i7 Intel processor today, it's probably identical in size to a Core i7 from 4 years ago, and it's probably physically identical in size to a processor from 8 or 9 years ago. Might just have less pins or more pins today, but punchline is that the physical size of these devices have maintained a standard for years and years and years because we have cases, ATX cases for our computers that the motherboard needs to fit into the case. Everything else needs to fit on the motherboard. We have this section for the CPU. This is how much room we have for the CPU. Fine. If you want to have a multi-CPU motherboard, that motherboard then gets larger and it no longer fits in a standard ATX case. Now it has to be you have to get a case that's capable of holding that larger motherboard. So we have some standards. Now, when it comes to them making a graphics card, those standards are out the window. They don't have to make the thing the same size as it was before. They can make this graphics card as thick as they want to. They're basically just saying, okay, well, the super high-powered card is going to mean that you only have one PCI Express thing plugged in. Nothing else will fit inside of your case. And this is going to take up all the power as well. So, then you have these situations where people have, multiple cards. So that's inside of a computer. The whole thing's graphics card. So kind of the punchline is that these guys they don't have to play by the same rules as people who are building their own computers, or like Intel has to play by. When Intel designs the next Core i7 processor and their next architecture for it, which we'll talk about kind of what that means, when they design that, they are starting off with, here is the footprint. This is the real estate I have to work with, because that's what my users need. Okay? And they're probably also starting with the number of pins. If you just built a computer this year, and next year you decide you want to upgrade the processor to the latest Core i7, maybe this year you go with a Core i5 just to kind of get started, you're budget pleasering it or something like that, and then your plan is to sell it, and you're going to come into some money around Christmas, and you want to upgrade it to the latest Core i7, you don't want to have to swap out the whole motherboard, right? So reasonably speaking, as long as your motherboard is within a couple of years old, you probably can run the latest, greatest processor. Every now and then there's going to be a jump, right, where they have to make a decision that a processor is a new architecture that requires more pins. They can do more things, and you put more pins on it, all of a sudden now it doesn't fit inside of the thing with less pins from before. So we will run into those, but generally speaking, we don't have the issue of visitors. Generally speaking, we don't have the issue with having something physically not fit in a modern motherboard when we go to upgrade the stuff. Same thing with RAM. Our RAM has been the same physical size for many, many years now, right? The RAM gets faster internally, so we're able to access the individual elements of the RAM more quickly, has a higher clock speed on the RAM. That's kind of the interface between the RAM and the motherboard, let's say. So how fast we can communicate with that shared resource that is the RAM, that has increased. But if you put the fastest memory, fastest RAM on the table from today, and you put the fastest RAM on the table from 3 years ago, physically, would they look different? Would you be able to tell the difference at a glance? Probably not. Probably not from the same company. Physically, they're the same size. They'll fit in the same slots. The idea is we have some standards as it comes to consumer PCs, but when it comes to graphics cards, that kind of all goes out the window.
Give it 2 years. Once DDR4 becomes more mainstream.
Well, fair enough. So we always have those jumps, but those jumps are typically few and far between. Let's take our hard drives for today. So since we're not going to talk about hard drives too much, let's just have that discussion right now. So even though the current trend in hard drives is the solid state drives, right? So it's getting the price down, the capacity up, and then also continually to increase the speed, but the speed's already fast for solid state drives. So that's the big craze right now. But solid state drives are using the same hard drive interface to the motherboard that hard drives have used for the last 10 years. They're using serial ATA interface to the motherboard. So nothing's changed. Make sense? So at some point, what's going to happen is we're going to say, okay, well, this serial ATA cable can't send data any faster without melting. Okay, the cable will get too hot and will melt. So we need a new technology to be able to send more data in parallel or something like that. So what do we need to do? Well, we can't make it backwards compatible anymore. As long as we're not maxing out this, we can keep working with the two ends. We can keep making our solid state drive faster, knowing that our motherboard is going to be able to handle speeds faster than this cable in between can. But as soon as this cable starts becoming our bottleneck, where our equipment is able to deal with stuff more quickly than that cable can, now we need to swap out the cable to something else. We had that for years and years. What came before serial ATA? So we go to hard drive stuff.
Same kind of logic like when we made that switch from USB 2 to 3.
Well, something came before serial ATA. Okay, grayish looking ribbon. So IDE. So IDE cables came before serial ATA. Now, we could say before, it actually was slightly before, but in kind of competition with each other during the IDE craze, we had another technology. IDE is here, let me kind of jump all over the place here. Let's talk about parallel versus serial. All right. So this is more of a generalistic technology, and it's related to computer hardware in general. We kind of have two different philosophies on how we can transfer data. Philosophy number one is we can transfer stuff in bursts. That is parallel. So parallel, and let's just kind of keep it a standard since we're going to be doing a lot of bits and bytes and discussion during our second hour today or whatever. So let's call this 8-bit bursts. Right? Parallel technically doesn't say it has to be 8 bits, but let's just use that for easy math right now. Okay? Serial is 1-bit bursts. So this is really linear. Okay? So when we send information in parallel, we're sending it in bursts of 8 bits. When we send information using a serial communication channel, we're sending it 1 bit at a time, one after another. Right off the bat, what could you tell me is the difference between these two in terms of the problem of putting the data back together on the receiving end? Okay.
But the serial would be just in a constant line of it being in order when it comes out.
Serial, we're sending it in order and receiving it in order, right? It's guaranteed in order, and we don't have to do any extra work. Okay. What about parallel? Parallel, we have to decide how we're going to split it to begin with, right? How do we choose which 8 bits to send, and then how do we reconstitute the stuff on the other end? It's extra work. Right? So now you have work at the beginning and at the end. And what are we gaining? We're gaining the ability to send 8 times more information at once. Where's the trade-off? Which one's faster? Do we have a prediction? So if we were choosing a hard drive technology, would you rather have a parallel or a serial hard drive technology? Okay. Is your answer something other than the fact that modern day it's serial ATA? Or is that exactly what it's based on?
You got to think that there's going to be some sort of processing information when you send it back, or when it gets sent, so that it knows what order, so that it would take longer to rearrange it, and you'd have to rearrange it more often.
Okay.
Rather than not having to rearrange it at all.
All right, so So these are kind of, go ahead before I say this. Give me your take.
Well, you'd have to read 8 things at a time, and then send those 8, or you would read one, store that, read a second one, store that, read a third one, and then when you have 8, send those. You're reading it off the disk linearly.
Okay. So now let's kind of connect a couple of dots before we take we'll take a break like in 5 minutes or so, since we kind of got a little bit late start. But let's connect the dots to something I said a few minutes ago. Our job when we're trying to pick a technology to use for something is to pick whatever is going to be the fastest, right? Do you suspect that fastest may mean parallel sometimes and serial other times, specifically through history of hard drives? Okay, so, just in the last minute, we've been kind of talking about some of the extra work we might have to do. So you were kind of talking about, well, with parallel, we're reading things, chunks at a time, writing things chunks at a time. Serial, we're reading things bits at a time, so single elements, atomic bits at a time, versus sending 1 bit at a time. So now we have to think about, well, what's the cost of reading and writing? How expensive is that to read 1 bit? Am I doing a lot of extra work to read 1 bit at a time rather than 8 bits at a time? Is 8 bits at a time 8 times slower than 1 bit at a time? You see what I'm getting at? And the answer is it depends. Look at the history of these technologies. This all goes back to things interfacing with the motherboard using some sort of cable. There's an interface between these guys. We just looked at these graphics cards. So this is an interface right here. This interfaces with the motherboard. And this guy is using the PCI Express interface, which has been around for a while. Right? So PCI Express, which they've upgraded a couple of times, but it has a speed associated with it that they keep trying to push farther and farther and farther. But the idea is that we're going to have to go to a different interface for these as soon as this graphics card is trying to send data faster than this guy can transmit it. And this guy can receive it. Make sense? The bottleneck can't be that transmission medium. So, but we've got to think about the endpoints. So that graphics card needs to be able to send information down through the PCI Express slot. The hard drive needs to be able to send information. When information is requested, it needs to be able to send it over whatever interface it's connecting to the motherboard through. So when we look at the history of this, parallel versus serial, we talk about it in terms of our hard drive. Serial ATA, this guy is as you might expect, a serial technology. IDE, what do you think, parallel or serial? Okay, parallel? Why? Is it a guess, or do you base that on something?
Well, I guess one of the reasons would be inside that. Just looking at a ribbon cable, you can tell there's 8 different cords going through it.
More than 8 actually for that, but yeah. So lots of pins, lots of stuff. Okay, yeah. So the concept is it seems like it's a division of labor type of technology, and it is. So this is parallel. All right, so kind of in competition with IDE, it actually came out a little bit before IDE, I believe. There is a serial competitor to IDE. Anybody know what that is? This guy was the ultimate don't conform to standards. SCSI? Have you seen that before? You know what it stands for? It's a good. It stands for Small Computer System Integration. That will not be on a quiz. It's more just trivial knowledge because I'm old. But back in the days of SCSI, it was horrible because you had SCSI, you had SCSI 2, you had super slim SCSI, you had ultra wide SCSI, you had ultra SCSI 2. So not all SCSIs were made the same. What's this? So, the idea is these were all based on serial. So this is a serial technology. And they were similar to parallel in terms of speed. Now, so let's go back and think about the kind of the time period for this. Let's look at maybe the year 1998. So 1998, we're dealing with SCSI and IDE. Okay, how old were you guys in 98? 4. You're maybe a little older. How old were you? 5. Oh, not really. Oh, so you just graduated. Yeah, gotcha. Right. Yeah, old Alex. He was probably 11.
It's Vietnam. They don't release certificates.
They count by bamboo length.
Every time the baby's born, they plant a tree. And that's all they know.
All right, how old were you in 98? 10? I was a little older than that. Yeah, I was. So in any case, what was I getting at with that? Okay, so back then we had SCSI and IDE as competitors. So just based on what you know now, we'll have a deeper discussion about it after we take a break because I don't want to drag this on too long. But just based on what you know as of right now, which is knowledge you kind of walked into the room with, what kinds of applications do you think we use SCSI for, and what kinds of applications do you think we used IDE for? They both existed. They both were used. Okay. Well, okay. No. Yeah, you got to keep in mind that point in time. I mean, laptops were pretty primitive, so they were having to work with whatever they can get into a laptop. Yeah, oh yeah. I mean, laptops were expensive and heavy and no battery life. That was back in the nickel metal hydride batteries.
Expensive, light, and no battery.
They weren't light.
I'm saying now they're expensive. They're light.
Oh, relatively speaking, laptops are dirt cheap today compared to then. Yeah, and that's going to be kind of a discussion we're going to have after break as well. Okay, so laptops is the wrong answer. What kind of applications do you think we use SCSI for? Well, I mean, what are our options? You know, when we think about computers today, if you go out and buy a computer, and so we've already decided laptops, so portable computers aren't a thing. So we go back to 1998. You were either buying a computer for personal use or as a server, right? All right, so kind of one is it's a single user interfacing with this computer. Another one is we're going to have multiple users interfacing with this computer at the same time. So SCSI was used for server class machines. IDE was used for personal class machines. Okay. Now, I'll just ask this question. We won't answer it until we come back from the break. So, which was faster? Think about that during our break. All right. So, it's 7:08 right now. So let's come back at 7:18. So take a 10-minute break, whatever, and I'll start getting the first video uploaded.